Like it's start time. So I'll say it again, but I think all of you guys have got it figured out. If you haven't already grabbed your tests, they're over there, so grab that now. I'd like to take a little bit like we've done on the other ones and a chance to go over it. Remind you of your calculations. I'll start with the median and the average score on test number 3, which is never an easy exam. I probably don't need to tell you that. I'm sure you figured that much out yourself here, but actually pretty high scores for test number 3. And because as you know, test number 3 is. So I always feel like I got to start test number 3 and say, hopefully that didn't wipe you out mentally too badly, because it always is a hard one. But you guys as a class anyways, as a whole, were better than the scores we normally get. So these are some pretty high average scores, and so some of you did quite well. And of course, some of you didn't do quite so well as typical. So I want to take a minute here to kind of go over them, and maybe go over them quickly, because here's kind of this goal. We've only got 2 more lectures here. So we got 2 hours today and then 2 hours on Wednesday. And that's the end of the lecture. And then we've got the final exam, which is a week from today. So this time, within a week, you will be halfway done with your exam. So remember, Monday morning, what time did your final start? 8 o'clock, okay? So it's an hour earlier than normal, if you will. So 8 to 10 is our time frame, and we can squeeze in a few more moments after 10, but it's best not to plan on it. But I know we can, because I know the next class starts coming in at about 10:30, so we can kind of work down that road and get most of our stuff out of here by 10:20, and then kind of squeeze out of here at about 10:30. So anyways, so here's the plan. I'll take this first time to go over the test. Hopefully it won't take too long. We'll do, but you know, it's well worth it, especially if you missed a few points here or there and you're not real sure what it was about here, or you missed some. Want to make sure you have a chance to at least have the ability to go back and then redo it and look at it, because typically on this third test is there's always something somebody misses, some little point here. Maybe it's minor for you, and that would be a good place to be, but chances are it could also be quite major. This was some significant stuff and significant work we've done. So if there are a few things that you don't quite get, hopefully this will at least get you on the position that you can then understand them as you leave the class, and you can either ask me questions or Don questions or the tutor questions or whatever the case may be, or maybe that'll give you enough just to kind of figure it out on your own. So that's the plan at first. Then we're going to go back to chapter 13. If you remember, we were working with 13. We almost finished that 13 on Wednesday, and we got a little bit more to talk about satellite motion, and then we'll go into 14. 14 is kind of a switch of gears. It's a good place to kind of switch and say, okay, this is our ending. We'll go into fluids. So you can see we do have an aquarium and some fluids up here. We'll be talking about it. So that's what today's lab is about here, our last lab for the semester, on Archimedes' principle. And so hopefully we'll get a chance to talk about Archimedes' principle. Perhaps not, but that'll be fine. We will talk about it in lab and then on Wednesday. And then the last thing is Bernoulli's principle. So simply put, we're going to wrap up 13, go into 14, and we're done here. Let me say this as far as homework. Your last assignment to turn in is chapter 13, okay? I know I handed out the sheet for 13 and 14. Wasn't sure how far we would get. We never do get far enough into 14 to really make it worth, I think, doing the complete set of homework. And so you're kind of open-ended on the homework. You don't have to turn in the homework for 14, but I will say this. This is the final exam. 1 week from today, you will have 5 questions throughout the semester, the chapters 1 through 12, the meat of the material, and then you will have 1 from chapter 13 and 1 from chapter 14. And as you'll see as we get to 14, there's 2 principles, an Archimedes principle and a Bernoulli's principle. So obviously it's going to be one of those 2. All right? So I'll say it again in case you didn't hear that. 5 questions next Monday from the bulk of the class, which is chapters 1 through 12, and then 1 from 13 and 1 from 14. Chapter 13 is your last assignment to turn in. So turn that in sometimes this week, preferably before Wednesday, since I may not get to it or see it before then. But if you are squeezing through and pressed with time and you can get it to me by the end of the week, that's fine too. But don't take it through the weekend, okay? Don't turn it in later. Number one is I want to get things done this week, but more importantly, you don't want to be messing with old homework. You want to be studying for the final exam. That's what this weekend is going to be for you. So final exam. And so come Monday morning and 8 o'clock and be ready to go with the final exam. So I hope that makes sense. Any questions? You good with that? Final coming up. All right, we're going to go over the test now. Finish 13, going to 14. Final exam, 8 o'clock next Monday. 5 questions from the bulk. 1 from 13, 1 from 14. Okay, last homework assignment to turn in is 13. Sometime before this week is over. Turn in all those homework. Use the weekend, study, study, study. And of course, obviously, you have other tests besides just this one. All right, well, if there's no questions on that, that summarizes the rest of this week. And then crunch time, I guess, is this week, really. And then next week is finals week. And then, well, 6 weeks off for the semester break. And then we'll be back at it next semester. Let's look at number 1. Hopefully you caught it right away. We went over a lot of these. We were doing collisions, and this is a collision involving both conservation of linear momentum and conservation of angular momentum. And so that was the key. Hopefully you caught that. I mean, what I was writing on the board was things like, is linear momentum conserved? Is angular momentum conserved? Is energy conserved? And so if you remember some of the examples we did, we asked ourselves that question. And the condition if linear momentum conserved was, yes, it's conserved if there's no outside influence, no outside forces. Is that the case here? Yes, it just says you have a rod floating in outer space and 2 objects come and hit it. So if you take your system as the 2 objects and the rod, no outside forces. So yes, linear momentum is conserved. So hopefully you did something like this. The first object weighed 400 grams and it was traveling at 10 meters per second. The second object was also 400 grams, but it was traveling in the opposite direction, and so it's negative, and it was only traveling with 7. And so hopefully that's kind of the first thing you did. What is the linear momentum? Then they all stick together. And so these 2 objects stick to the rod, and the rod itself was what? 1.5 kilograms. So 1.5 plus 2 times 0.4 times the final speed. So there's step 1. If you put this all together, you got a 1.2 on this side of the equation, you got a 2.3 on that side of the equation, and got 0.52 for the speed. So there is step 1, a Chapter 9 problem, if you will. It is conservation of linear momentum. But also fitting into this problem was a chapter, I guess this is 11, conservation of angular momentum. Is angular momentum conserved? And again, we went through that. Yes, if there's no outside torques. And again, this was set up to be in outer space, so both would be true. And so we can do our conservation of an angular momentum. R cross P for the first one added to an R cross P for the second one should give us our angular momentum for the 2 objects as they were coming in. And so if you're looking at the little diagram there, we've got the 2 objects coming in. And of course, a tough one, and what I emphasized is, could an object traveling in a straight line have angular momentum? And yes, it can. And so we have it. And the first one then has a distance of 0.2 is where it hits. It has a linear momentum of 0.4 times 10. And if it's a cross product here, maybe I should draw a picture here, but if we calculate it around this axis, then this would make it go in a clockwise direction, and so that's a negative angular momentum. The same thing with the second object. It was down below. It was the same distance down below, so the distance is 0.2, its mass is 0.4, its speed is 7, and again, doing a cross product means it goes around in a clockwise direction also. And so that is our angular momentum, at least before the collision. And so if we put those two together, we get 1.36. And I suppose I should watch my units. This is a meter, this is a kilogram, this is a meters per second. So this is kilogram meters squared per second for the units. And then likewise, this brings us back into chapter 10. Chapter 10 is how do you calculate the rotational inertia. And in this case, we've got the three objects. We've got the 112 ml squared for the rod itself. And then we've got the two blobs, if you will, and they're just sitting at a distance away. So if we put in those numbers, we get a 1/12. The mass of the rod was 1.5. The length of the rod is 0.8, and we square it. The two blobs, as we've already done, are 0.4. I guess I should call them clay. They are 0.2 out, and then you get your omega. So again, the only unknown here is the omega. This all calculates out to be 112, and the units for rotational inertia are kilogram meters squared. So of course it comes out to be 1.36 kilogram meters squared per second over 0.112 kilogram meters squared, coming up with an angular speed here of about a 12.1 radians per second. And so there's problem number one. Conservation of linear momentum, conservation of angular momentum. Should emphasize it again. 6 ideas that we've learned this semester. The only 6 ideas you need for this semester: Newton's 3 laws of motion and the 3 conservational principles. So there they are: conservation of linear momentum, angular momentum, and energy. But we don't even need energy for this one. And in fact, when I originally wrote this question, get ready for the test, I did say, like our example problems, you know, what fraction is converted into thermal energy, which would bring us one more step. And anyways, as I was proofreading it the night before, I go, maybe that's just too much work. I mean, this stuff is already hard with a lot of work. So I'll back it off one and say I won't ask them for the fraction. I'll just ask them for the speeds, with the idea that if they could do the speeds, they should be able to also do the fraction there. So anyways, and I think it made a better test question too, because then it divided it in 2 parts, and it got me a chance to see, okay, which half do you know and which half do you don't know, or do you know both halves, or you don't know either of the halves. Number 2, this is rolling down the hill. I got 2 objects rolling down the hill. And we did a problem like this, except the one we did in class was, what is the speed at the bottom of the hill? This one goes one step further. This one says how much time does it take to travel down the incline. So we've got to do the speed, and then we've got to do the time it takes. And there's many approaches to this. I didn't even realize. I mean, I figured when I wrote it out there were many approaches. And then I got to realizing after I was doing it and grading, I said, wow, there's even more than I had thought. So you may not have done it this particular way. This is certainly the way I had envisioned, because we had done speed and we had used energy to get speed, and then we could take one more step to get time. So I'll let you decide how you wanted to do it. But if you did do it this way, I would have done it with the terms of energy and said, look, the initial energy is equal to final energy plus any heat that's created along the way. There's no heat created because there's no sliding going on. This was our discussion about something rolling. It's all a static friction. That's what makes it roll. And so we can start off with mgy initial. And so this ball starts at the top of an incline. It is going to roll down and then be down here somewhere. So at the bottom here, if we call the center of where the ball is y equals to 0, that means back here at the beginning, what I can do is say that this starts then at a height of, does it say the height? 0.3, yeah. So 0.3 actually, and it's kind of at the edge there. And they say that that's a 0.3. And they also say this is a 1.2. But starting off then with just that term here, what we have is then an M, a 9.8, and a 0.3. And so that's what we know to start with. Where does that energy go? Well, it goes down the hill, and so we know that it has some translational kinetic and some rotational kinetic. And you might recall what we did in class is we first converted the rotational speed into a linear speed. So that what we can do is take the V out we could even divide by an M and put the 2 on the other side, so this becomes 2.9.83. And that would take out the 2. It would also take out an M. And so what we have is 2 times 9.8 times 0.3, and then we would have a 1 plus, and I'll write it as I times, or I divided by mr squared is equal to v squared, because we've got two different objects. I1 is going to be the solid sphere, and I2 is going to be the hollow sphere. So we had those two objects. So we would put in different values. So V1 then would become 2 times 9.8 times 0.3 all over 1 plus 2/5, and then take the square root. Whereas number 2, the hollow one, is going to be the 2 times the 9.8 times the 0.3 over 1 plus the 2/3 times the square root. So the solid one is going to be going a little faster, 205 meters per second, compared to the hollow one, 1.89 meters per second. And so that's kind of a step one. What's the speed at the bottom? But again, it's not the only option, because this is done by speed, and you certainly could have done it by forces and acceleration and torques, although I think that's a lot more work. Maybe not. It kind of depends on how you think about it here. It's just because the fact that you have friction in here, but the friction goes to making it rotate, it's easy to forget about friction in your free body diagram. But it was good to see many of you did it that way, did it successfully that way. But my thoughts were this way. This is what we analyzed in class. This question asks for a little bit further the time it takes to travel down there, and without knowing the acceleration, that makes me think of kinematics equation number 4. And so this is the one that comes to my mind here of, hey, let's use kinematic equation number 4. It's the one that doesn't have the acceleration. However, if you had done this by forces, you would have acceleration. So then you might want to do one of the other kinematic equations. You do have to do a little bit of work with Pythagorean theorem here. Of course, since we know the dimensions of the triangle, we're going to have to do a little bit of work to find out how far it moves down the hypotenuse, and it's about a 1.24. So putting that into here, 1.24 equals initial speed equals 0, final speed equals 205, at least for time number 1 being the solid sphere. And so time number 1 comes to be 1.21 seconds. whereas the second object, 1.24, starts out at 0 and only gets to 1.89 seconds. And so we'll call that time number 2. So it's a lower speed, should take a little bit longer, and it does, and comes out to be a 1.31 there. So that's kind of the 2 steps for the 2 separate objects. First, get the speed, and then second, use the kinematic ones. Or if you'd already done the kinematic ones, then you would have that also there. So whichever way came to your mind first. And so, and then you can do it in terms of either, you know, torques, and it depends what you picked to calculate your torque. Did you pick the center of mass, or did you pick the contact point? And be careful, some of you mix those. You pick the contact point to be your calculation of torque, and that's fine. In fact, I would recommend it. But then you did the rotational inertia about its center. So you just kind of left off the parallel axis theorem there. So be careful if you see that md squared written there on your paper. That's probably what happened to you, is you forgot to do the parallel axis theorem. Yeah.
When you have a 1/2 m plus at the very bottom. Yeah, that one.
Yeah.
When you have a I over m squared, you're dividing by m, so you can factor out the rest.
Yeah, there's an m here and m here. So when I divide by the m here, that goes away. It goes away there, and of course then it goes downstairs here. And again, this would be the first time you had done it. You may not realize that, but what was real nice was this step, because we were going to give I in terms of m, so it was nice to have it eventually in terms of the m. But of course, I know where I was headed with it. You might be just better off right here back at the I to have plugged in, and then you would have an m in every term, and then it would just cancel away. Because there is no m listed, so somewhere along the line you need to realize, uh-oh, the m's going to drop away. Well, let's go to number 3. Number 2 probably turned into be a harder one than number 3. Wasn't designed that way, but based on the point distribution, that's kind of what I would say, and maybe just number 3 because it's right from chapter 12 there, which didn't have any of the new physics of it. You guys seem to just kind of nail this one right from the get-go, or get the idea. Here it is. Here's what I would call the free body diagram. And not that you have to redraw it again. I already have it there in the problem. But you want to make sure you draw all the forces on here. And of course, one of them is, I'll call it an M1G. That's the weight of the beam. And the other one, which I'll call an M2G, is the weight of the person standing on the beam. In addition to that, we have the tension in the cord. And in addition to that, we would have some set of resulting forces, Rx and Ry, or Fx and Fy, whichever terminology you want to use here. But there's the problem, is we've got the weight of the beam, we've got a person standing on it, we've got it angled down, and they show the angle here at 30 degrees. They show this angle at 110 degrees. And I think one of the trickier parts of problems like this is just getting your angles straight, which angle applies where and how here. But I'm hoping the first thing that I saw was something that looked like this. What about the sum of the forces in the x direction? What about the sum of the forces in the y direction? And what about the sum of the torques rotating around a z-axis? Well, since it's in equilibrium here, I guess the answer is 0, 0, 0. And so that's the first step. And really the main step here is that all these forces better add up to be 0. And so as you look at this, I would say, okay, here's this first one. This first one has an Rx going that way. This has no x component. This has no x component. This one you might want to break apart a little bit. It would mean this is 20 degrees. And so if I take a t and I take sine of 20 degrees, or for that matter, cosine of 70 degrees, in that negative direction, I get my 0. So there would kind of be my my first equation of these three, and maybe the easiest of them, is to say, okay, there's what happens with the x components. Y component, very similar. There is a vertical component from here. There's also a vertical component here. This would be t, and this I would write as cosine of 20 degrees, or if you prefer, sine of 70 degrees. But that's a plus also. So these two are lifting up, the tension here and the vertical component here. These other two are pushing down, so it's minus an m1g and minus an m2g. That has to equal 0. And so there's your second equation. And then finally your third equation, and really the most helpful one of the three to begin with, because when you calculate your torque here about this endpoint, so call this about point A, so if I calculate my torque about A, what I get then is only the unknown t in here, and that's really the key to the problem. Now once I get the t, I can jump back up here and put it here to get Rx, or put it here to get Ry. So as I look at my torques, I guess I would look at this first one. This first one then would have a weight or a force of mg. Its distance would be half the length of the beam. I don't know what the length of the beam is. Fortunately, though, it's going to show up in every term, so it doesn't matter. And then I need to decide if it's a positive or a negative rotation, and the convention is it's negative. It's making it rotate in a clockwise direction, so there's my first torque. Same thing, oops, almost left off something very important here. That's the force, that's the distance, and then I need the sine of the angle between them. And so if we draw a line out to here, we can see that, hey, we're looking at that angle there, which if we draw a dotted line, that's 30 degrees. So this is sine of 120 degrees, or although I guess that's also sine of 60 degrees, as some of you put, and it's also cosine of 30 degrees, as some of you put. So take your choice there. Depending on your viewpoint, you may use 60 degrees, 30 degrees, 120 degrees, whatever. Same thing about number 2, mg, and then this one is 4/5 of the length L out. And also the same thing, it would be a sine of 120 degrees, or the sine of 60 degrees, or the cosine of 30 degrees, whichever you prefer. But both of these make them go in a negative direction. It's the other one, the tension, so it's plus t at a distance L, sine of, and this is the one you got to be a little more careful in watching your angle here. See, this is R coming out here, and this is 30 degrees there. So if this whole thing from there to there is 110, 30 more make 140. So this is the sine of 140. Or for that matter, it's the sine of 40 if you would prefer to do that angle in there. But again, like in the lab, notice it's the angle between R and F. It's not the angle on the horizontal. It's not like with the force components. And so those are easy to get backwards. And so hopefully you saw that in the lab, and you saw that into the homework there. Well, if you work out this last line, you'll see that there is an L in every term, so we can cancel that off. And as we put everything in here, the only thing that is unknown is the T, and so this comes to be 1828 newtons. And so there's the T. And then once you've done that, coming up to here, the first equation would give us Rx, which is 625 newtons, and Ry comes out to be then 438 newtons as we substitute them back in. But it's that first part that, hey, they're in equilibrium. All the forces, all the torques got to come out to be 0. Okay? Now the next one, actually the next two, are not in equilibrium. So we're not going to have all the forces coming out to be 0. These two are actually moving. And the first one here, I think, is a little easier than the second one, but both of them aren't easy at all. They are, you know, I think the tougher stuff that we've done this semester. And I would start here with your free body diagrams. And so, same comment that I said before, some of you aren't doing your free body diagrams. And I think you're ending up shooting yourself in the foot here. Not that, you know, I'm going to mark anything wrong if you didn't do your free body diagram, but there's, you know, just mistake after mistakes being made, and I can just, you know, I just can't help but wonder, going, you know, if they just had a picture in front of them, I mean, I don't think they would do this, but, you know, maybe I'm wrong here. But as I look at the free body diagram, if I take this first one, which is 1.5, it's being pulled up by T1, it's being pulled down by 1.5 G. The other little block, which is the 2 kilograms, is being pulled up with a T2 and it's being pulled down with a 2G. Where then the disc is then tied to it, so the disc is being rotated one way with a T2 and being tugged on the other way with a T1. And it's those 3 pictures which is going to lead to those 3 equations, which then we solve those 3 equations to get the answer that we're after. What is T1 and what is T2? I would start with this one. Maybe I would also should say I should just start with the decision on which way you want to call positive. I'm hoping you see that with the larger mass over here compared to the smaller mass over here, that what ends up happening is the larger one goes down, the smaller one goes up. There's a rotation in a clockwise direction. So maybe we should call all of that positive. And if we do that, then we would go T1 minus 1.5 G equals 1.5A. That might be equation number 1, since it goes up. But making sure my signs are consistent, then coming down is positive, so it's 2G minus 2T is equal to 2A. That would be probably equation number 2. And that way my A's are the same. They're both positive and they're the same amount. And that's some old stuff. I mean, that goes all the way back to chapter 5. That's our free body diagram with linear motion. What's new is this one. This is the torques. So when I add up the torques, I would set it equal to I alpha. And so that's really what I was after. This is the chapter 10. This is the new piece of the puzzle. And so you get a torque over here, which is 2T times this R, this radius, minus a T1 times the radius. In order for my sign to be consistent with those, I will call a clockwise a positive. Now, I suppose we could have called all this negative too, so that works fine. If you want to call that a negative, fine. Just make sure you do the same thing over here, or just, you know, be careful with your signs. And then it equals to I alpha, and so that's a 1/2 mr squared, and the alpha then is an A over R, which is kind of nice because one of the R's goes away and then the second one goes away with that over there. So it becomes T2 minus T1 equals to 1/2 the mass, and the mass of this disc was 3 kilograms, so it's 1.5A. I'll put a box around that. But as I look at this, I've got an equation, an equation, an equation. 3 equations, 3 unknowns. And there's different ways of solving them. You can solve this and put it into here to get rid of A, whichever approach you like best. But in the interest of time, let me not actually do the mathematics. I actually solved this for T1 and put it into there, and that for T2 and put it into there. Now that I look at it, that might be the long way to go, but nonetheless, I did, and I got A equaling 0.98 meters per second squared for the acceleration when I did that. And then once I did that, I can come back up to here then and put in for T1, which is about a 16.2 newtons, and a T2, which is a 17.6 newtons. Okay. And interesting enough, I would say a very common mistake on this one. No, I guess it's the next one, not this one. Never mind. But now that I brought it up, I'll just kind of remind you, does the tension in the cord equal to the weight of the object? No, I think I said that a lot in chapter 5. And I hadn't said it for a while because I don't think anybody really made that mistake on the first test. So I was like, okay, they got the idea here. But that did happen a lot here in number 5. I saw that a lot where people just assumed the tension was equal to the weight of the object hanging. And that's not the case. And so finally, the last one, the grand finale of them all. You might even remember me working this out. This is an exact copy of what we did in lab. In terms of hanging a weight and letting it spin. Although it's not, I mean, we got the moment of inertia by an experiment in the lab. This one you're supposed to calculate it to get alpha. So in that sense it wasn't quite the same as the lab. But the setup is exactly the same in the lab. In the lab we measured alpha to find I, and this one we calculated I to then find what alpha is. But you had this object that was spinning around, and the object looked something like this. It was a rod spinning about its center, and put on top of it then was a disc or a cylinder. And the cylinder wasn't spinning around its center. And you could either do it at the beginning or later on, but I think you kind of realize that you're going to need the rotational inertia here. So maybe I'll just do that first. I would say I then, total, is going to be these two objects. It's going to be the cylinder and it's going to be the rod. I'll start with the cylinder. The cylinder is given there on the front page as 1/2 mr squared, but don't forget that that's about its center, and this is not rotating around its center. It has been shifted over a little bit. The distance d that it is shifted over is the radius of it. And so this comes out to be 3/2 mr squared then for the rotational inertia of the cylinder. So that's a big step right there. In addition to that, we've got the rod. The rod is about its center, so nothing too new there. It's just the 1/12 ml squared. So as we put in the numbers 3/2, we need the mass of the cylinder, which is 250 grams. The radius of the cylinder is 7 centimeters. So there's the numbers for the cylinder. The rod has a mass of 300 grams and has a length of 60 centimeters. And so when we put all that together, it's 0.0108 kilogram meters squared for the rotational inertia of the system. So we've got the rod and the disc. And so that's a step that, like I said, you may not realize you need quite yet, but it is gonna show up there. So whether you do it now or do it later doesn't really matter. So but it's not an easy step, and so there's one significant step. The main part of it is the free body diagram stuff, and a number of you drew an aerial shot on it. I like that. That was kind of nice here. You said, okay, here's the rod. Here then is this rotational point with the cylinder right on top. So you did something like that. And then you go, well, but underneath it then is this pulley system, this disc, and it's being pulled here with some tension T. And so that made a nice free body diagram, where what you could say then is that as you look at the sum of the torques and set it equal to I alpha, you could say the torque is the tension in the string times this lever arm, which was 0.1, equals I, which is 0.0108, and there's alpha. So there's the first free body diagram. And that's for just the rotational motion. The other free body diagram is that little cylinder that is causing all the pull here. Its tension is here and it's being pulled down by mg. And so as you look at that one, you would say, and just to be the direction the same here, as this unwinds, calling alpha positive, let's call then downward positive. So this is an mg minus a t equals to an ma. And so what's kind of nice in this is that this a is alpha times the radius of this torque arm as it begins to unwind. But I must admit here, what makes it pretty hard is there's a lot of different R's here. I mean, there is an R for the cylinder, the 0.07. There's the length of the rod. I don't know if I'd call that really an R, but the other one is that torque there. That where is it tied to? So you got to make sure you put the correct 0.1 distance and then the correct 0.07 distance at the right place. But once you've done that, it makes it kind of nice over here, because then the tension is, and if you divide by a tenth, that's 0.108 alpha there. And you can put that into here. So this becomes 0.05 times 9.8 minus 0.108 alpha for that term. And so then this is 0.05 alpha 0.1. And so the only thing, you know, unknown in there is the alpha. And at 4.33 then radians per second squared then is what that comes out to be there. So again, the two objects in the two free body diagram and substituting them back and forth. But like I said, if there's probably any common mistake, it was really easy for some to stop right here. And yet even though over here on this one, you didn't say that the tension was equal to the weight, somehow there were a number of people here saying the tension was equal to the weight. So, but it's not. The tension doesn't equal to the weight. If the tension equal to the weight, then this side would all come out to be 0. We would have no acceleration for either one of these. So we can't have it coming out to be 0. So there's the test. Like I said, if, hopefully that makes a little more sense to you, gets you to the point that you can work through or at least ask some, you know, questions about it and say, okay, I want to make sure I get this straight now, because as you said, it's not easy to get it right the first time, and I didn't get it right on the test, but I want to make sure I get it right on the final. So make sure you ask about those. So, and again, wanted to emphasize, don't, even if you didn't do so well, but on the class as a whole, you guys did well for this third one. It's just, this is just one of the tests that I never know if it's better to say something before the test or just wait till afterwards to say, it's just, it's the nature of the material. I did think I said at the beginning that, we will get up to the hard material. It'll build up and build up and build up. And we got there. And last class, I told you to take your right hand and put it over your left shoulder and pat yourself on the back. Because truth be told, I don't know if you did well or not. Just the fact that you were able to get through that one is a big hurdle in and of itself. And then the material that we'll do here in 13 and 14, again, I wouldn't say it's easy, but it's a lot easier than those problems that we've done. All right, well, let's go back into chapter 13 then. And so that took 40 minutes. I that wasn't too bad. I thought it might take a little bit even longer than that. So, but I think time well spent here. So let's do this then. If you recall, we were talking about this new piece of information. And in this chapter 13, this new piece of information was discovered by Newton. Has to do with the force of gravity between any two objects. And so I was been joking, and I'll say it again, that you want all the answers to all the problems. Here they are. This is the force between any two objects. And so we started real simple. Then we asked, what if it was 3 objects or 4 objects? But I think one of the harder ones was really the energy. And so the energy is worth discussing in great length. And we did. We did discuss the energy. And we talked about an object being shot up, and let me make sure I got my units right this time. I think I used 2,000 meters, or I used, 2,000 meters per second is the right number, and then I put kilometers here and kind of messed that up. But the whole point is we use that to get the escape speed here. And let's look at then the energy then of a satellite. And that's really the last step here in this chapter here, is we said, well, this was the energy we would need to escape. That's kind of where we left off. We said if you fire something really, really fast, in fact, maybe I'll put it over here. We had velocity, and I don't know if we put a little ES for escape speed, but we came up with this equation. We said 2 times G times the mass of the Earth divided by the radius of the Earth. That is how much speed you would need to escape the Earth. And we got out our calculator, and we did one for Earth and we did one for Mars, and had a little discussion about that. And then we said, well, and this is where we left off. We said, well, why do we always launch these satellites as far to the south as possible? And the idea is it takes a lot of energy to get up there, and so the Earth is already spinning to the east, so take advantage of that. And so let's talk about that. How much energy would it take to get a satellite up to those heights? And let's not even make it as complicated as saying the Earth is already spinning, because then we'd have to say how much energy compared to what latitude we are on the Earth. And so forget that for a moment. Let's just say we are starting on a Earth somewhere on the surface. We won't consider the spinning of the Earth quite yet, and I don't think we'll do anything that includes the spinning of the Earth. But we would have to ask this question. We'd have to say, okay, so if here you are, and here's the Earth, and we're going to put a satellite up here, that satellite has to be moving. That was the key step into the problem. The satellite's got to move. If it doesn't move, gravity will pull it straight down to the Earth. Is there any gravity way up there? Yeah, how come it doesn't hit the Earth? Because it's moving sideways, right, with enough speed here. And so what we concluded here is that the force of gravity, because of the motion of the satellite, results in it being an acceleration that makes it turn instead of an acceleration that makes it go faster. But what we had set up is that the force of gravity, which would be G times m1 times m2 over r squared, would have to equal to m2 v squared over r. And so we put together, if you remember on last Wednesday, this new piece of information together with some old information from chapter 6. And we said the two masses would cancel off. Oh, I'm sorry, there's no r squared down there. And one of the r's would cancel off. And we said this, that the speed of a satellite then would have to be that much as it goes around. Notice that number then is smaller than this number. So this is what we did last time. At the very end, this is how much speed it would need to completely escape. We're not completely escaping. And so it needs this much speed. Less than that. Not that much less than. So to get the satellite up there, depends how high up there it is, this would have to be its speed. And what was interesting is the higher it goes, the slower the speed is. And what I wanted to point out is that doesn't mean it needs less energy, because as we're going to see, the higher it is, the more gravitational potential energy. So it still takes more energy to put something up higher and higher and higher. But it's not because it needs more speed. The speed actually way up there is not that great. And we even mentioned that. I think we were comparing the moon way out here, taking 28 days to go around, compared to the International Space Station, which I was going to look that up here. Bummer. I forgot to do that, see what the time period was there. But somebody mentioned they thought it was 7 hours. And could be right. It seems a little high, but I'm not real sure. I do know this one, though, that there's two really nice places to talk about. One of them is way up here that would take a period of 24 hours to go around. What would be nice about that one? Yeah, we call that a geosync satellite. I didn't bring the globe out here this time, but maybe I should. But remember, if that whole Earth is taking 24 hours to go around, then a satellite up there would kind of look parked, if you will. You could put it right over, say, the equator, halfway between the east and west coast of the United States. So we often say over the equator south of Texas. You parked it right there, it would remain essentially in that position. And many of you have those satellite dishes, the DirecTV or the Dish Network. And that's what you're doing. That's what you're pointing at. They've got their satellite up there, and they've got it, you know, situated right there, and it's moving technically, but it doesn't really register as a movement to you, because it goes around in 24 hours and you go around in 24 hours. So you put up the dish, you mount it to your rooftop, you angle it up, you clamp it down and say, there it is, I'm pointing right at the satellite, and the satellite's not moving. Well, not true. The satellite's moving, but so are you. And so these geosyncs are a nice one. If you've looked at weather satellites, it's the same thing. You park one over the Pacific. It's always taking a nice aerial shot right down on the Pacific, and we can see any storms forming because the westerly winds then blow it, you know, into us. And so we've got this good picture of it. And so it really helps to have all that data. You can see what's going on. For the days of satellites, you always had a more accurate weather prediction on the East Coast than the West Coast, because the storms came from the land, and so you already had data. You had data as it came across the United States or sweeping down from Canada. And so you had all that data. It was much easier to predict what was going to happen in New York and Washington, D.C., because we knew what was happening in Minnesota and in Washington and in California. We had that data, but we didn't know what was going on in the North Pacific. And now we do far greater, and so our predictions of our weather are actually pretty good. And another one of my favorite ones is this one right here. It's a little bit lower. I guess we could run through the numbers here to find its height here, but it's not quite 11 hours. It's not quite 12 hours. Although for the moment, why don't we just call it 12 hours? But it's not halfway up, but let's call it half the time anyways. That's a nice one going around that 12-hour cycle. So it makes one revolution in roughly 12 hours, or 2 revolutions in one day. But that's the GPS system. So if you guys have any of those GPS, if you ever used the GPS system, they're nice. That's where the satellites are set there, and they're going around here. The fraction less than 12 hours is because you want to get the satellites back in the same place every day. And maybe I need to draw a picture over here for that to make sense. You got to remember, here's the sun, and if here's the Earth, and you have satellite number 1, satellite number 2, satellite number 3, and satellite number 4. A day later, I'll exaggerate the Earth's movement, but a day later, here's the Earth. So at noon, we were like this. This is noon again. This is 24 hours. But satellite number 2, to get back in the same spot as viewed from outer space, is not 12 hours. I mean, 12 hours is half a rotation, or 24 hours is a full rotation, only from sun to sun. And a full rotation is not quite from a sun to a sun. So really one rotation of the Earth is viewed from the outside is not 24 hours, but it's 23 hours, 56 minutes. So it's 4 minutes shy of what we think of the revolution, because we are on the Earth and we moved with the Earth, so it's a perspective. Well, maybe I, again, better not spend too much time on that, but all I wanted to do was to point out here that we can have different speeds again when we're at different points, and we saw that last time. But what I'm going to do is then just calculate the energy, because if this is the speed, then I can do this. What is the kinetic energy of this satellite? And so how much kinetic energy do we have to give the satellite? And so in this case, it would be A1/2 times m, and the speed squared would look like this. In fact, maybe I should put a 2 here, coming back to this notation to say, okay, 1 is the planet you're going around, and 2 is the satellite. So it could be the Earth and the satellite, but of course it could also be the sun and its satellites. Maybe it's artificial, I mean it's natural satellites like the Earth here. But what you come up with is G m1 m2 over 2r for the kinetic energy of this satellite. Now, what's the potential energy? Well, the potential energy is what we did a lot with on last Wednesday. And so I'll just put that back up there. And so there's the equation for the potential energy. And of course, we did a bunch of problems where we started on the surface of the Earth and went up. Now, the satellite would be at a much greater height or distance from the center than just the radius of the Earth. But when I go to put these two together and ask this question, okay, what is the total energy that is needed? It looks like I've got like terms, and that's helpful because it really simplifies things for our final equation here. If you simplify that, you can see that here you have a G, an M1, an M2, and an R. But here we have a half, and here we have a -1, so it ends up with a -1/2. And so there's the answer to my question I was looking for. How much energy does this satellite have to have? And so that's its total energy it needs. Now maybe I should pause. Is that a positive number or a negative number? Negative, right? Because what do we say about 0? What was 0? Yeah, 0 is a lot of energy. It's how much energy you need to escape. Okay, so it's worth saying it again. Remember, the reason we calculated this much speed is this is the speed you would have to give an object so that you'd give it so much energy it would never come back. What is that total energy you'd have to give it? 0. That's how much energy you have to give it. Okay, so again, it sounds funny, I know, but that's why I keep emphasizing it. These are negative numbers. And so starting on the surface of the Earth, you would probably have, without a spin, starting on the surface, you would start with a -G m1 m2 over r radius of Earth. So that's how much potential energy you have. And that's a very large negative number, if I can say large negative number. But that's extremely large in its negative sense. So to get the satellite up into this position, you have to add to it to get to this much potential energy. Okay, and this is a lot less negative. So just you got to lift it up. That takes energy. Plus you got to get it moving. That takes energy. So the total energy has to come out to be that. Okay, and so that's how much energy it would have to have. In fact, why don't I finish the chapter this way? I'll put some equations on the board. We've seen this equation. This is the first one we saw. But then we saw this equation. And then we saw this equation. And then we saw that equation. And then we saw that equation. Wow. And the part that was supposed to make this chapter easy might make it hard. They're very simple equations. So closely they look the same that it's a recipe for disaster here. So what do each of these mean? What's this one here, this first one? Yeah, that's where we got started. That's the Newton's universal law of gravity. Everything is actually derived from that. So if nothing else, know that one. That's the whole force of gravity here. What was the next one? Yeah, that's the acceleration. That's the force divided by the mass. That was the acceleration on that planet. And so we talked about, how that comes out to be 9.8 on the Earth, but a different number on Mars and on Venus and on Jupiter and wherever. How about that one? Yeah, that's the hardest one we spent the most time on, I think. That's the gravitational potential energy. We got that by doing the integral. So we did the integral again. It's too bad and maybe I'll put it in a little arrowhead. That's that mgy. Oh, and maybe this is the mg. So remember, use the mg if you're in the atmosphere. Use the mgy again if you're in the atmosphere. But for big changes, we've got to go to the more accurate one here. And this is the gravitational potential energy. And then we talked about it. We can no longer pick where we want to call r equals to 0. We had that option here, no longer here. So where does r equal to 0 here? Yeah, at the center of the Earth or center of the Sun if this is the whole solar system. And then the two new ones we see here today here, what are these? Yeah, that's the kinetic energy when it's in an orbit, so I guess I should put kinetic energy of a satellite. What's this one here? Yeah, and that's the total energy of our satellite. That's not just the potential energy or just the kinetic energy, it's the total. So the two together is a total energy. And it's negative, it's not enough to escape there. And so those are a series of equations that unfortunately are so similar and so close that I feel like at the end of the chapter I should just throw them up there on the board so that you'll hopefully not mix those together now that you see how closely they are here. Well, I'm going to move forward into chapter 14 just because I'm a little concerned we may not have time to do any direct calculations from the back of the book. I'm hoping I still will, so I haven't ruled it out, but I'm going to kind of wrap this chapter 13 and 14 together and see where that leads us then on Wednesday. And so once I get the material all out there, then for whatever balance of time we have left on Wednesday, that's what I'll do is examples. And like I said, we'll do as many as we can as time will allow. But like I said, compared to the other chapters, I think this one won't be quite so overwhelming. I think you'll get the idea much easier, and the examples aren't quite as significant here. And so now that it's good, it's 10 o'clock and we've got an hour now and then 2 more hours on Wednesday here. Let's look at our final chapter. And this is the one where I have been saying that we get into fluids for the first time. And fluids is kind of interesting here because really this chapter had all been about mechanics of solids. And for the first time here, now we talk about fluids. And no way in one chapter at the very end of the semester do we really do justice to our fluids. And we're not trying to. All we're trying to do is point out, what if you carried these same principles off to things that are not solid? They're not rigid. and different parts can move at different speeds. How would you start to handle that? Because many of you, when you transfer from here, will go on to, say, UCSB. And one of the first classes you'll have to take when you transfer is often called fluid dynamics or fluid mechanics. And so you've got to study the motions of your fluid. So you take all these principles that we just learned and we start applying them to fluids. So again, this chapter is not in any way to be a substitute for a full class on the mechanics of fluids. What it is to kind of make that bridge between, okay, what have you done now with the easy stuff, which I'm sure after this last test you're thinking, yeah, that was the easy stuff, okay. And how does this stuff that doesn't change its shape and all the pieces move at the same speed, how would it get more complicated if it was a fluid? Where as it spins, it can change its shape, or as it moves, different parts can move at different rates. What do I do then? And it does become quite difficult. And not a surprise, the math level really skyrockets. It's part of the reason why we don't try to really do too much fluid mechanics. We're waiting for you to get your math education to a point that you can have the math skills. So just like many of you took me for Physics 102, but didn't immediately come into here because you had to build up that math skill. You said, look, you've learned the basic physics, and the next step is not more physics. The next step is mathematics so that we can do some harder physics. So some of you carried from 102 last semester right into here. Others of you, you had me for 102 a year ago, or maybe even more than that, as your math skill built up. Well, the same thing can be said here about fluid mechanics. I need you to understand, before we can really do too much fluid mechanics, these wonderful equations you're going to solve in your Math 220, that differential equation class here. So you guys are working towards that, and your day will come where you will be experts in your differential equations. In fact, you will look back on your Calculus 150 and your 160 that you might be struggling with right now and kind of laugh and say, God, I wish I could do that easy stuff again here. But it's a lot like this test you just took. Do you remember the first chapter? Converting our units? Wow, yeah. Or that first test. You know, ball is dropped. How far does it fall after 3 seconds? And it may have seemed difficult when you first got it. But compared to what you've done now at the end, that's simple stuff. And same thing's going to happen in a couple of years from now. You're going to look back at this and say, oh yeah, the stuff where it was solid, that's easy. Now, let it change its dimensions and let it change its size and let the different parts move at the different speeds. Well, that's kind of my introduction into fluid mechanics. So here's what we're going to be looking at. And I want to emphasize this from the get-go because I think too often when people hear the word fluid, they immediately think liquid. And that's not what's meant by fluid. Fluid is the molecules can flow past each other, they can move. And so does that happen in a liquid? Oh, absolutely. But does it happen in a gas? Yes. And this weekend with the winds, you probably noticed the flow of the gas molecules that were in the air. They flow past each other. They flow around things. And so just like you can have currents flowing in a river or a lake or the ocean, you can have the flow of gas molecules too. And so here's our fluid mechanics for today. I've got liquid, yes, but I've got gas too. Okay? And so I've got both to show you and to work with here. Okay? And so that's our start. Now, a new quantity, at least kind of for us here, is pressure. We'll use capital P for pressure. Now, I'll say new, but it's not new. You saw this already when we did our fluid mechanics stuff in 102. What was the definition of pressure? Anybody remember? Yeah, we defined it as a certain force over a certain area. Well, you can imagine what we're going to do now at this level, now that we've gone from 102 to 121. And I asked this, well, how much area? Is it the whole area here? Couldn't it just be a little area? And then couldn't we take that area smaller and smaller and smaller, right? Until it's just a point, so wouldn't it be the pressure there? And there, 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 right? And if you wanted to know the total force, I mean, couldn't you add up the pressure over the whole thing? Right, and so not a surprise, we will not write it as force divided by area, but we will write it as the limit as a small amount of area goes to 0, and so we will have a little force and a little bit of area, and so our definition of pressure will be dF dA. And that's what will be useful for us. And so you can rewrite it then as a little bit of force equals pressure times a little bit of area. And so if I were to ask this question, what is the total force on this glass piece here? Well, couldn't I just take the force here plus the force here plus the force here plus the force here and just add it up? Which means what? Yeah, so the total force would be the integral of the little forces, and so it would be a P dA. And I don't know if that helps. I'll put a box around it, but that would be then the total force, adding it up. Now, of course, the simple case is, what if the pressure is equal to a constant value? What does that become? Well, if pressure is a constant, you can pull it in front of the integral, and you just get pressure times area. And so doesn't that look like the simple case? Doesn't that look like the physics 102? We just took pressure times area. And yeah, that is the easy case. It's not the very realistic case. It's the whole reason why we wanted you to learn calculus before you came into here, because we know that there are many times where the pressure is not a constant, and the pressure can vary. In fact, that'll be our first calculation here. We'll see that the pressure can vary significantly between the top of the fluid and the bottom of the fluid. And hence, if I want to know how much force is on this piece of glass right now, I've got to realize then that the pressure here is different than the pressure here. So if I took the same size area here and the same size area there, would they be pushing the same amount? No. And so to get the total force, I would have to realize that down here is a lot more force than up here. Anybody ever see the cross-sectional view of a dam? Hoover Dam, for example. Sometimes we forget it because we stand up on top, if you've ever been on Hoover Dam, and it looks something like this. There's a road up there. The concrete is probably 20 feet wide or something up there. You've got the water on this side of it, and you've got this drop over here on this side of it, and you stand up here and you look over the side and you go, wow, this is a big dam, right? I mean, this big wall of concrete. But what does it look like on the other side, the part underwater? Why? There's a lot of force right here, and you need a thick wall to handle all of that force pushing there on that. And so the wall gets thicker as you go down there. It's got to be really, really thick. And so this, of course, is not that deep, so the thickness of my glass doesn't change here, but the thickness of my dam needs to change dramatically. And so I think mentally we just see that. We see this wall here of this dam, and that's not going to hold it. This will bust through here, and so we've got this thick thing down here, and we look over there. And so there's kind of the shape of our of our Hoover Dam there. Well, that's the reason for all that. So you are hopefully getting what I'm after here, which is this new quantity called pressure. And if pressure then, together with our calculus, will look a little more complicated than the stuff we saw in 102. And we can calculate that. And I'm going to here in just a second. But before I go further, I wanted to come back here and say, okay, what are the units for pressure? Do you remember that from 102? Or maybe you see it now. Wouldn't it be force over area? So what was the unit for force? Newton for area? Square meter? And so we give it a name in honor of the great scientist working in the field. What's this? Yeah, Pascal. Good. So we'll call this a Pascal. So when we talk about the pressure, we will say so many pascals. Now, many of you are probably more familiar with it in terms of the English system. What do we do for pressure in the English system? All right, PSI, which stands for? Pounds, there's the force, per square inch. So it's the same idea. It's a certain amount of force in a certain amount of area. Pounds per square inch. And so we're really doing the same thing. Well, I haven't really kind of derived it for you, but I guess I've made the statement. Doesn't the pressure increase as you go deeper? Which is what I was trying to indicate with that aquarium. It's what this quick little dirty experiment is for. Here I have my water, my lake of water, if you will. Is the force at the top of the dam the same at the middle of the dam, the same at the bottom of the dam? And it's not, is it? You can see that the water down here, doesn't it shoot out at a faster rate? And so there's our pressure being pushed out there. And so this kind of illustrates it quite well, that the pressure is not the same. But it gets, I think, even more interesting than that. Because it's a fluid, it doesn't have to be straight above it. Look at this one. This one, you can see the water coming shooting out, but the water is over here in my left hand and the hole is over here on my right hand. If I lift it up, doesn't it shoot out at a higher rate? And if I lower it down, isn't it at a lower rate? And so the pressure has to do with that height difference. And so of course we want to give somebody an IV, you have to put it, up here so they get some pressure. Doing this can be dangerous. All you do is take your blood and send it into the IV, which you could, I guess, bleed out there in terms of going to the doctor's office. But closed up there. But there's the idea. Let's get some numbers here. Okay, let's look at this fluid here. Let's go through a little mental experiment here. Let me kind of erase this. And you can kind of calculate how the pressure would change in a fluid, whether it be a liquid or a gas, although the gas is going to be a bit more complicated. So you're going to see that we're going to wait till next semester before we do some more with the gases. But for this one, we can do right here and say, I want you to kind of take a mental picture of that box of water right there. And let's take a look at chapter 12. In other words, I look at that box right there. Does that box of water, is it going up? Is it going down? Is it rotating? It's in equilibrium, right? So what do you know about the sum of the forces and the sum of the torques on that little box? It's zero. And we don't even need to look at the torques for right now. Let's just do the sum of the forces here. And so if I take that little box right here, and I imagine that little box sitting in that aquarium here, and so let me just call this the height of the aquarium, y. And let me call y equals 0 for a moment. And why don't we just call down positive? So in other words, let's measure my my distance as from the height down. You know, how deep am I in the fluid? 1 foot, 2 foot, 3 feet, you know, whatever. All right. And so I'm going to use, you know, kind of the unconventional coordinate system. Instead of calling up positive, I'm going to call down here negative. But if I look closely at this box, and I would say, well, what's pushing on this box? Could you do the free body diagram here? Yeah, so what's pushing on it? Okay, I heard somebody say the weight of it. Okay. So I would put the weight right here, mg. Okay, fair enough. Anything else?
Water from the bottom, the sides, the top.
Okay, this is that whole idea that the water is pushing on it. And somebody said the water at the bottom and the water at the top and the water at the sides are all pushing on it. And I would agree. And isn't that what we meant by the word pressure? Isn't that why this water goes shooting out? When I open this up, why does the water shoot out? Isn't that because the water next to it is pushing on it? So those of you who said the water is pushing on it, yes. And those of you who said the pressure, yes. And those are one and the same. And that's what I wanted to point out here, that we've got this pressure pushing on it. In fact, what I would say is right here, there would be some kind of pressure. Let me call this pressure at Y. And then let me call this the pressure at, and it kind of depends what symbol we want to use for thickness. How about if we call the thickness of the box a delta Y? So this would be the pressure of Y plus delta Y. So that would be the pressure there. Because it really comes back to this statement here. How much force do I get? And I would say that there is a force right here. This force, which I might call the force on the top of the box, would equal to the pressure at the top of the box times the area of the box. Whereas this right here, I would call the force at the bottom of the box. And that would equal to the pressure at the bottom of the box times A. So I would say, yes, you're right. There is water pushing on. Water is the pressure. Okay, so if I look at this, I see three forces so far. I see the weight of it. I see the water on the top pushing it down. I see the water underneath pushing it up. Left and right, I guess I have them too, but I'm not going to worry about them, because is it fair to say you think they'd be equal? Right, and what I want to know is what happens in the up and down motion anyway. So not worrying about the left and right, not worrying about the torques, just the up and down. These are the three forces. Now help me out here. I bet you can guess. Do you think the force at the bottom, lifting up, is the same as the force at the top pushing down? Do you think one's bigger than the other? Yeah, why? Which one? Why? Okay, but I guess I'm just back to this experiment here. Isn't this what we saw? Isn't the pressure increasing with depth? And that's really what I'm trying to derive here. I'm trying to derive what would that number be, but I saw it in the experiment. So this right here is telling me that I think that number is bigger than that number, which I guess kind of makes sense, because look what happens when I add this up. The sum of all the forces in the y direction have to be 0. All right, so what's pushing down? Yeah, wouldn't you say it is the pressure at the top times A? That's pushing down. The weight, mg plus. So those two are pushing down and calling down positive. So the top is pushing down, gravity is pushing down. What's pushing up? Well, the pressure at the bottom times the area. And so there's my three forces. But now I'll do a little bit of arithmetic. together with some algebra and some calculus, and I should have what I'm looking for. Watch this for a moment. I'll move this to the other side. This is pressure at the bottom times A minus the pressure at the top times A equals mg. I'm going to divide both sides by the volume of the box. Now, it may not be obvious why I would want that now, but look what it comes out to be. Look at this side of the equation. What is mass divided by volume? So that's density. We've been using the symbol rho for density. So that's one side of my equation. But this is the more interesting part. Volume would be area times its thickness. And so this area would cancel off. And what I have then is the pressure at the bottom minus the pressure at the top divided by delta y equals rho g. And once I've done that, then I can do my calculus. Because what if I think of this as a really small box? What if I then say, well, to get the equation where I'm not even having a box there or thinking about it, what I'm going to do is take the limit as delta y goes to 0. Pressure. And maybe I should write it as y plus delta y minus pressure at the top, which is y, over delta y. Does that look familiar to anybody? Yeah, isn't that the definition of a derivative? So this is saying how does the pressure change with depth is equal to rho g. And so I'll put a little box around it because that's my first statement that, hey, this is how the pressure changes. In this case, it is increasing. That is clearly saying that the deeper you go, the greater the pressure. And it doesn't matter at this point whether you're in a liquid or whether you're in a gas. That statement is true. Now, here's where I will kind of limit our discussion to just liquids. What if the density is equal to a constant? We call this incompressible. In other words, take this aquarium again. Look at the density near the top compared to the density near the bottom. Are they the same? Well, if they're not compressible, yes. That is, if you can't get the molecules any closer, yes. And liquids are like that. If we go to the molecular view of these are little bouncing ball bearings that are pretty close together. And so when you squeeze them, they don't get much closer. Now I say much closer because technically, do they get closer? I mean, technically, are they a little bit compressible? Yes, but nothing like a gas. What is the difference on a molecular level between a gas and a liquid? Yeah, the liquid, the molecules are real close to each other. In the gas, they're bouncing off and there's a lot of space between them. So when you put pressure on a gas, what happens? Yeah, it compresses. It changes its volume. So when I go and make this step, I have just said that I'm kind of limit my discussion here to liquids. I mean, this would still be true whether it be a liquid or a gas. But as soon as I say this step, now I'm talking about just the liquids. And I want to emphasize that because we only have time really to talk about the liquids. But guess what we're going to do next semester? We're going to come back to that equation. in probably late February, I'm going to say, hey, do you remember chapter 14? Remember that last week of school back in November, right after Thanksgiving? And you're all going to go, oh yeah, I remember. You were telling us to remember, right? And remember I put that equation on the board? Let's redo it for gases. So we'll come back to this for gases, but not today. Okay? Late February. Meanwhile, we'll do it here for the simple case. The simple case is, what if it doesn't change? Because how do you solve that equation for pressure? How do you get pressure? Yeah, you integrate. So I will integrate. So I will integrate dp dy with respect to y, which means I've got to integrate rho g with respect to y. Now you can see why mathematically I said this will be the easy case. Because on this side of the equation I get p, and so the dy's cancel off and I get a dp. What do I get on this side of the equation? Yeah, if this is true, doesn't it make it an easy integral? Because it just becomes a rho g, and then I get an integral dy, plus some constant of integration, if you will. And so, for the liquids, and only for the liquids, here's what I'm saying. I'm saying the pressure is equal to this value that gains with depth. And so, see how y gets bigger, the pressure gets bigger. And so what we are saying here is, as you go down in a liquid, the pressure gets more and more and more and more and more. And that's why I did this little experiment at the beginning, so you can see with your own eyes that the pressure gets more and more and more. In this case, it increases in a linear fashion. As you'll see for gases next semester, it'll be an exponential factor. But it'll be some kind of factor that's got to be increasing according to that equation. And in this case, if it is incompressible, it is the easiest equation we could have. We should probably talk about this. What's this constant? Yeah, I heard somebody say it. Wouldn't it be the pressure when y equals 0? So maybe we should call that. We should call that then its initial pressure. I'm sure your author first writes it like this. He said this is a pressure when y equals to 0. Well, where does y equal to 0? Well, right here at the top of the surface. Why would there be a pressure here at all? Yeah, the gas above it, right? And that is an equation, like I said, we will solve later. So we will just call that the atmospheric pressure. What is the pressure right now in this room caused by all the molecules that are in my liquid? Well, our easy answer is we will just call it PA for the pressure from the atmosphere. But since it's a gas, we will study it in more detail. But I need a number. And I bet many of you know, what is the atmospheric pressure? Yeah, let's do sea level, since we are at sea level, or pretty close to it. And I know it changes a little bit with altitude, which is, again, why we'll be doing this in February. What would it have been if we were not at sea level, but we were up in the mountains? We would have a different one. And it changes with atmospheric conditions a little bit, but it's only a little bit. So, and I heard a bunch of people say it because there are different units. I heard one person say, well, it's 1 atmosphere pressure. Okay, true, not useful though. We want it in pascals. What is it in pascals? It's 101,300 pascals. It's about 14.7 psi if we wanted to do it in the English system there. Okay. But the point is, it is a number, and then the pressure increases. Probably not a surprise to you if you've ever been swimming and you dive deep in the pool. You will quickly notice the pressure change. You don't have to go that deep, 6 feet, 7, 8 feet, and you can start to feel it on your ears right away here. And so it's not that, you don't have to go that far down in order to feel a significant pressure change. In fact, we'll put in some numbers here and ask this question. How far would you have to go underwater in order for the pressure to be twice atmospheric pressure? I mean, to get atmospheric pressure, didn't you have to go down in the atmosphere about 100 miles plus? How far in the water do you have to go down? Well, let's see. So, atmospheric pressure is 101,300 pascals. My question for you is, how deep would I have to go in order for that to be twice as much? So if I double this, this is 202,600 pascals. Rho G Y. And there's my question. Why? How deep do I need to go into this lake in order for me to have what we would call 2 atmospheres of pressure? Double that. And it's surprisingly not that far. Now, probably deeper than you're going to go on a normal just swim and dive, but it's really not that deep. So if I put in some numbers, I will subtract that. So we're looking at 101,300 pascals here. I need to know density. Ooh, there's a good question. Part of the reason I wanted to do this is my first example. What is the density? Okay, I heard somebody say 1 gram per cubic centimeter. Absolutely right. Not very helpful for this one because I got kilograms and meters. So let's switch it to kilogram. What is it in kilograms and meters? And that may not be as common. That's why I wanted to make sure we went through it. Shall we do a conversion? Back to chapter 1. Wouldn't this be centicubed, meter cubed? Centicubed is 10 to the minus 2 cubed, right? So doesn't that make a 10 to the 6? So we've got 10 to the 6th grams per cubic meter, right? So isn't that 1,000 times 1,000 grams per cubic meter? And so isn't that 1,000 kilograms per cubic meter? All right, so if you don't already know, here's the density of water. It is 1,000 kilograms per cubic meter. That's the density of water. That is the same as 1 gram per milliliter or 1 gram per cubic centimeter. And then if I put in my 9.8 meters per second squared, I can now solve this for y. And somewhere around 10 meters is what I have here. So 101,300 divided by 1,000 divided by 9.8 and 10.3 meters. Okay. Must be close to about 33 feet. So 33 feet, 34 feet, something like that. So how deep do you have to go here? Okay, to change by 1 atmosphere in pressure. So it's not that deep. And that's why I say the density here is so much greater than the atmosphere. And again, I wouldn't want to use this equation to do the atmosphere because it's not fair. But if I could probably roughly say the density of the atmosphere is the same for 10 meters, you know, between here and the 2nd story and the 3rd story. But I better not, otherwise you think I'm going to use that equation. But I'm kind of curious what a change in atmospheric pressure would be at 10 meters. So it's not going to be that much. In fact, it would be probably about 1,000 times lower because I know that the density of air is 1.2 something instead of 1,000. And so there's 1,000 times less changes. That's why to notice the pressure on your ears, you've got to go thousands of feet. I mean, if you've ever gone, up a pass and drive in the mountains, you'll feel it in your ears when you go thousands of feet, but not tens of feet. But in the water, you'll feel it as much as 5, 6, 7 feet. You'll clearly see that. Well, this gets me to the main point I wanted to do here, which was to make sure, could we calculate the force on this piece of glass? And I think we could. It's going to take some calculus, because is the force down here the same as up here? No. But how about the force here, which is, say, 2 centimeters down, compared to the force over here, which is 2 centimeters down? Same. So maybe we should do this. What if I were to divide this whole thing into stripes and say, could you calculate the total force here on this? How would you do it? Yeah, could you come up with your own integral on your own? Are we there yet? Is this the 4th or 5th time this semester I've asked that question? We're going to need that skill next semester, right? Can I take what I know, apply the calculus, come up with my own equation? And we have it. I've since erased it here, but I would say that the total force then on that aquarium would be the integral of the pressure times the area. And I got to add it up. And so maybe it's worth drawing the face of that aquarium on there and ask this: what is the pressure and what is the area? Well, the reason I was drawing stripes on there is because I'm hoping you'll kind of see that in a single stripe that maybe has a thickness of dy and a length L, wouldn't the pressure be the same across that stripe if we made the stripe thin enough? And so that's what this is. If we take the pressure as a function of y, so the pressure at that one depth, we're going to take it real thin, the area would be its length times its dy. And I am going to add it up from 0 to, well, maybe I shouldn't do a y. How deep you want to call this? Length. What?
8 inches.
Yeah, I don't want to put a number though, but h. Let's use L this way and h that way. So 0 to h. And so now I can put these two concepts together. One being the definition of pressure, the other being what we derived here using the whole idea that the net force was 0, and I got that equation for pressure. And so what I have is an integral from 0 to h of atmospheric pressure plus rho gy times L times a dy. So the first term would be atmospheric pressure times L. And then when we did an integral, that would be a dy evaluated from h to 0. The second one, though, would be a rho, a g, an L, rho g L. And when I integrate a y, I get a y squared over 2 evaluated from 0 to h. And so atmospheric pressure times L times h times rho times g times L times h squared over 2. And so there is the force that I am getting from the water. And we can put some numbers in here if you want to. But it's probably worth talking about a little bit more here. Now, this is the water pushing out. Anything pushing this way on the glass? Yeah, and there would be the air molecules here. So I guess in all fairness, I shouldn't say that this is the net force on the glass. This is just the force the water is pushing out. Wouldn't the air be pushing back? And if we could say that the pressure here doesn't change by much, then we could probably say that that term which is caused by the atmosphere pushing down on the water, which is then pushing out, is the same as the atmosphere on this side. So if we do that, we could say, well, what's the net force? And so I would have this PALH, and then I would have this rho times this G times this H squared over 2. But then I would subtract off this pressure from the outside, which we will just call atmospheric pressure, times its area, which we will call its length times its height. And so the net force on the glass is rho G H squared over 2. In fact, maybe I shouldn't even call it net force because I'm still not done. Are there other forces here? Well, clearly, yeah, this piece of glass is then glued onto here. So maybe I should just call this, I don't know, what am I trying to say here? Force. Maybe this is force from the water. This is force from water and the air. Because I do know if I did the whole net force, what am I going to come up with? It's 0. I mean, I can see that there's no acceleration to the piece of glass. So I guess what this tells me then is this is how much force I am getting pushing out between the air and the water. Hence, the glue that is holding these glass pieces together better supply that much force pulling it back in. Otherwise, this water would separate it out, right? And so then I would kind of have this, you know, this peeling effect, assuming it peeled from the top first. I don't know, it could peel from one side and shift that way. It could peel from the top. You know, I guess there's all kinds of ways it could peel from it. And given that there's more force down here, it almost makes me think if the glue's going to come loose, it's going to be down here. But this kind of looks like it holds it in there too. So, but I'm hoping you would see that idea. Now, if I wanted to put some rough numbers in here, we can kind of see what this is on the glass. Somebody said this was about 8 inches. So let me go ahead and put the density is 1,000 kilograms per cubic meter there. G is 9.8. To my height, let's use meters instead of inches. What are we looking at? 20 centimeters. So I'm going to put a height of 20 centimeters or 0.2 meters and square it. And this will give me a number at least to work with here and say, okay, this is how much force the water is pushing on that glass. So 1,000 times 9.8 times 0.2 squared divided by 2, coming up to being about 196 newtons of force. So it's really not too much force. Doesn't surprise me. It's not that much water. If this was a big lake, then this would be different. I wouldn't expect that piece of glass to hold back something, something much deeper than that. But that's enough for something that deep. If any of you've ever been to some of these aquariums that got deep tanks, I mean, you can just see how thick the glass is. It's enormously thick so that it can hold it there. And or more if you got the weight of Shamu laying on the glass too, then you want just not holding the glass, but the weight of Shamu as he bumps into it and whatnot there. But let's try this one. I don't want that piece of glass to move, so I'm going to calculate the force and make sure the glue is that strong. But it's not just move in a translation, isn't it rotate? So could we calculate the torque here too? Shall we? And it's certainly a much harder calculation, right? Because we got a force that changes, and then we've got a torque, a distance that changes. Of course, we have to say torque about what point. So and I don't really care here, but I think the bottom might be a little bit a better discussion here. So let's imagine right here that it was, you know, actually kind of as it looks, it's got this baseboard on it, and this board's not going to let the glass go pushing out, no matter really how much pressure we push down here. What's going to end up happening is if it does come loose, you know, this is going to stop it and it's going to kind of rotate. So let's calculate how much torque do I get. And so we're back to this problem here, but I'm going to maybe change my view to kind of a side view here and say, okay, here's the water line, and I'm going to calculate it about that point. So about this axis right here, what is the torque? Well, I would agree the net torque is going to come out to be 0 because clearly it's not rotating. So apparently between the water that's in there, the air on the outside, and the glue that is between those sheets and even in addition to this board up here, that obviously the net torque comes out to be 0. So I'm not going to get the net torque here, but I would like to know this. What is the torque from the water and the air? In other words, what does my glue have to compensate for in order to hold this aquarium together? All right, so with that in mind, and maybe I'll put red stripes in here too, what I will have is that same idea. I will have a stripe and a stripe and a stripe and a stripe and a stripe, something like that, right? And each stripe will have a thickness of, like we did before, a dy. It will have a length L, and it has the same pressure all the way across each stripe. And so I might think of it this way. A little bit of torque would be equal to what? All right, are we there? Can we come up with the equation on our own? So why don't we look at one little stripe here? Maybe this stripe right there. How much torque would you get from that one little stripe? Well, wouldn't it be the force from that one little stripe multiplied by the distance, the lever arm of that one little stripe? So wouldn't the total torque be the sum of all the torques from all those little, excuse me, all those little pieces, all those stripes? Does that make sense? And could you do it yourself? Okay. Well, let's keep going here, because I would say this then, that the force had an equation right here. It is atmospheric pressure times rho g y. And maybe I should have put this as pressure times a little bit of area. And the area was L dy. And then the lever arm is R. Does that make sense? So in other words, it's kind of like what we just did, isn't it? Where we're adding up. And the pressure gets bigger with depth. But there is something a bit more complicated and disturbing here. What's that? All right. So, I think you've noticed something here. These go together. What's R? I mean, I got to get these all the same variable to do an integral, right? So, look closely at what changes. as I do this integral, this doesn't change, this doesn't change, this doesn't change. Does this? Yeah. Does this? No. Does this? Yes. And is r the same as y? What is y? Y is the distance from the top of the surface down. What's r? From the bottom up. So r and y aren't the same thing. Related? Yes. Oh yeah, so we can probably figure this out before we go too much further. But we need to figure that out. We need to convert our r's into our y's, or our y's into our r's. I don't care which way you want to do it. But one's got to become the other. So before I go any further, why don't I do this? If I had gone down right here at this stripe, I would say that I am a distance y deep. I would also say that I'm a height r from the bottom. The two of those added together got to be h, right? Isn't that how those two play together? All right, so which do you want me to do? Convert everything into r's or into y's? Into y's? Yeah, kind of looking at the math, I kind of like converting into y's. Looking at the physics, I kind of like the r's. I like to start close to the axis and then move up. But all right, we'll convert. So that what that says is r is equal to h minus a y. All right, so that means what I've got now is an integral from PA plus rho gy L, and my r now becomes an h minus a y dy. And what are my limits of my integral? 0 to h. Exactly. And so there would be the torque from just the water. Now, maybe I'll have time to work it out, but I'm concerned that I won't. So let me stop there, because I don't think that's going to be too hard of an integral. I mean, yes, I have a binomial times a binomial, and so we've got a little bit of work here. We're going to have 4 different terms. Okay. But let's do this for a moment. What if we went one step further, kind of like we did with the aquarium here, where after we calculated the force from just the water, we could add the air to it also. So what would the torque from just the air on the outside? Do you kind of see that same thing? And again, let's make that kind of an overly simplification. Let's just say that the pressure from the atmosphere is the same everywhere here. And so we make stripes. Does that mean every stripe has the same torque, though? No, why not? Yeah, different r here, different radius. So again, kind of taking this aquarium and calculating that as its bottom point here and making stripes, I could go through the same thing. That the torque from the air is equal to the sum of the little torques from this the outside air piece. And the outside air piece is a force, a little bit of force on that little stripe times this r. And in this case, my r would, well, I'll hang on with my r, but my little bit of pressure would be the atmospheric pressure times the area, which I will call its length times its dy. And then r would essentially be the same logic, right? Where if you went down so far, you would be a y, but you would be up r. So why don't I write it so it looks the same, and I will call this then an h minus a y dy, and we're evaluating then from 0 to h. Now I say that because then it'll make actually solving this a little bit easier, because when I go, all right, what is the torque from both the water and the air? I can say it is that term minus that term. One is pushing it, you know, the water is pushing it this way. The air is pushing it that way. And it probably doesn't surprise you, just like in the force, the atmospheric part canceled off. Doesn't this right here look like this one, this first term? And so the only thing that's going to remain is the middle term, or the second term to that first equation, the rho gy times the L times the h minus the y dy 0 to h. Because we just double check, boom, boom, boom. Yeah, those are the same. So kind of makes sense that what is ultimately pushing the piece of glass forward, torquing it out, is really the water. I mean, yes, there's air above it pushing on the water, but that's equal amount by the air on the outside pushing back. So it doesn't surprise me at all that those cancel off. Just like over here, it didn't surprise me that these two ended up canceling off also. So then when I do this number, I can say, well, what remains a constant? A rho, a g, and an L. So those terms I can pull out in front. And so then I have this integral, which is h times a y, which I guess makes a h, and then we would have a y squared over 2 evaluated from 0 to h, minus, and this would be a y squared, so that becomes a y cubed over 3 evaluated from 0 to h. So when I put in my h here, I guess this is an h cubed over 2. This becomes an h cubed over 3. And I think that's a 1/6, if I'm not mistaken. That's 3h cubed minus 2h cubed. And so that's an h cubed over 6, right? So when I'm all said and done, I've got rho g L h cubed over 6. And so there's the torque between them. And I always like the part that it's got this h cubed in it. I mean, that number can get large. I mean, you know what a cube is. I mean, you take a 1 and you cube it, you get 1. You take a 2 and you cube it, 8. You take a 3 and you cube it, 27. So it doesn't take much depth here before all of a sudden we're talking about a significant amount of torque here. Well, anyways, I think we nailed the pressure pretty good. From there, it leads to Archimedes' principle. Oh, maybe that'll be a good place to stop. But that's today's lab even, is Archimedes' principle. So I'll talk more about Archimedes' principle in the lab here, and then we'll see it again on Wednesday.